Welcome to this video on deciphering the skeleton, focusing on the intersection of biomechanics, anthropology, and pediatric forensic diagnostics. Forensic skeletal analysis brings together three key disciplines to determine the origin of trauma. Forensic anthropology profiles the victim, biomechanics calculates the physics of injury, and pathology identifies the biological response to the trauma. Skeletal analysis uses layers of techniques. 3D imaging and reconstruction allows for non-destructive study. Finite element analysis simulates biological responses to forces. Stable isotope analysis deduces dietary habits and environmental exposures. Biological profiling often begins with dimorphism in the human skull. Male architecture generally shows larger overall volume, heavier bone density, and more pronounced muscle attachments. Female architecture is typically characterized by smaller volume and smoother cranial contours. Fracture timelines distinguish between perimortem and postmortem trauma. Perimortem fractures occur near death and exhibit smooth edges due to the bone's moisture. Postmortem fractures occur after death, presenting sharp, jagged edges due to the bone's dry, brittle nature. Vector mapping translates force to failure. A fracture's resulting pattern is the physical fingerprint of the impact. Blunt force creates radiating fissures, sharp force causes localized wedge incisions, and compression results in mid-shaft buckling. Comparing adult versus developing bone reveals significant differences. Immature pediatric long bone contains growth plates, which are the weakest points. Children's bones are also more malleable due to extensive haversian canals and an active periosteum, which aids in fast remodeling. The physics of plastic deformation highlights a child's bone's ability to absorb energy by bowing. Pediatric bone enters a state of plastic deformation, bending beyond spontaneous recovery without snapping, unlike adult bone, which tends to fracture completely. Incomplete fractures in children include bowing, buckle or torus, and greenstick fractures. Each type is defined by specific responses to axial compression and tension, reflecting the bone's elasticity. The statistical reality of pediatric trauma shows that while 42% of boys and 27% of girls will sustain an accidental fracture by age 16, a significant anomaly exists. Between 50 and 69% of all fractures in infants under 1 year old are non-accidental. Skeletal trauma specificity helps categorize injury risk. High specificity red flags include classic metaphyseal lesions and posterior rib fractures. Low specificity injuries, such as clavicular or linear skull fractures, are common accidents. Rib fractures are a high-value indicator of abuse with a 71% correlation in children. These fractures typically result from severe anterior-posterior compression, where the bone leverages against the spine. Forensic diagnosis is synthesized through the triangulation of intent, which considers three data points: the biomechanical force required, the child's developmental mobility, and the caretaker's account. Discrepancies between these points flag potential non-accidental trauma. The diagnostic protocol involves 3 steps. First, isolate the pathology. Second, calculate the mechanism and force magnitude required. Third, evaluate the context. Discrepancies between the injury's physics and the narrative indicate suspicion of intentional harm. Childhood can have painful consequences. Specific forensic knowledge is required to distinguish between injuries from normal behavior and those resulting from child abuse. As the Latin quote states, "A child should be given the greatest respect."